In this lecture, let us talk about linear models, which is one of the simplest and most straightforward data models that is widely applied in machine learning. As a rule of thumb, in practice, when you encounter any challenge, when you have the task, you should decide whether that is applicable. The linear models are applicable to the task. If they are, so probably your first attempt should go to linear models because they are somehow they tend to be stable. If they works, they keep working. So let's talk all the four elements in machine learning as we have discussed in the previous lecture with respect to linear models that are these are the data, the hypothesis. Obviously, linear model has defined a hypothesis family that we will use, and the error mirror, which is another name for criterion. Error mirror defines the task, and the linear algorithm of the weights, which are refers to the selection process within the linear model family. So first, let's have a look at the data. Linear models requires all data samples are represented in numerical values. For some problems, this is straightforward. For example, in the flower classification problem, each sample has already been represented by 4 numerical values. Although, when you look at a flower, it may have a lot of attributes. The color, maybe the smell, or any other appearance of the flower may catch your interest. But for to define a classification, a learning problem, each flower has been summarized into 4 specific numbers. And this task has been clearly defined for us. Sometimes we need to figure out how to define those features by ourselves. A less straightforward example is the image classification or detection of objects in images, such kind of tasks. The data consists of image pixels, and each pixel can possibly take a tuple of 3 values. Each value take in the range of from 0 to 255. We can convert those values into numerical values, of course. If we ignore that we have the discrete choice between from 0 to 255, we can just treat them as raw numbers, and we can concatenate, we can chain all the pixel values into a very long description, numerical description of an image. But as we will learn later, such straightforward representation of large data samples might not be working very very conveniently with linear models. So sometimes we'll adopt a technique called feature extraction. Like if we find there might be some particular interesting pattern we want to detect at each position of the image, then we want to apply this pattern extractor at every location of the image and use the extractor's response at each position as the features of the image, which is the idea behind modern deep learning algorithms in to do image processing. And another example is what we have discussed as language processing. We can convert each word into a word embedding, namely a numerical vector, so that such data can be processed by linear model family. So as to the hypothesis that is working on such data features, linear models is it cannot be simpler. Basically, the central idea of the hypothesis family is the value we want to predict is related to a linear combination of all the numerical features. So if you write down it mathematically, it is in this form. It's the product of the feature and a weight. Okay, the weight is what specifies the linear models we don't know before learning. This pair of products, we accumulate this kind of products over all numerical feature and weight combinations with the last with a constant value. Sometimes it's called bias. You need to distinguish this bias with the learning bias we will discuss later. So you just consider it's a constant value. This hypothesis can be written in a more convenient form. We can force each data sample to have an extra feature, which is a dummy feature. For whatever sample, we add an attribute. The attribute always take value 1 as a constant. And we just use another name to call the constant we add, tailing the combination of the features. We let it to be W0. So the operation of plus B now equals to increase the accumulation by W0 times X0, and the equation becomes very nicely denoted in this way. So if you remember something in your linear algebra, this kind of summation can be written in inner product of vector, a vector W. W is a vector of W0 all the way down to WK, and a vector X, X0 to XK. Remember that X0 always takes the value 1. So we will, later in our discussion, we will take whatever form which is convenient for us. Before we go to the next step, let us have an intuitive look at how such a hypothesis would look like. Consider if we have only 2 interesting attributes. By interesting, I mean those attributes are from the data, not including the X0, which we have said is a dummy attribute, always takes the value 0. So in this 2-dimensional data space, the value of a linear hypothesis, we haven't finished specifying what the hypothesis is. We just say, okay, the hypothesis is directly linked to an interesting value, and the value is the linear combination of the weights and the attributes, the features. Such value will not surprisingly look like a straight line crossing across the data space.